Hello everyone. Today we are doing section 2.1, the inverse sine, cosine and tangent functions. We're going to start with definition of one-to-one function. Definition. F of x, function f of x, is called 1 to 1, and I'm going to make it short, 1 to 1, if for every x in domain, if x1 is not equal to x2, follows that f of x1 is not going to be equal f of x2. Practically it means that if you take two different x's, they produce two different y's. So different x's produce different y's. What functions are one-to-one and what functions are not one-to-one? Function x squared, not one-to-one. Why? Because there are two different x's, for example, 2 and -2, which are producing same y, which is equal to 4. So x's are not equal, y's are equal. Does not work, not one-to-one. Another example. Cubic parabola, x cubed. You take any x and it's going to produce only one y. You see, x here, y over here. All y's are going to be different if x's are different. How do we check it graphically? Graphically, we check it using horizontal line test. For example, I draw a horizontal line here and I see that it intersects twice the graph. Any horizontal line on this graph is going to intersect it only once. So this is one-to-one function. Okay, let's do a review. Why do we need one-to-one functions? One-to-one functions have one special property. If f of x is one-to-one, it's going to have an inverse. Let me erase these examples of one-to-one and not one-to-one. And so, second definition. If f of x is one-to-one, and it has inverse. F inverse of x, which has domain equals to a range of f of x, and a range equals to domain of f of x. So, what does it mean? Range and domain are exchanging. F of x had something like domain, axis, and had something like range, y's. And it was moving like this. Now, inverse function is going to use y's as domain and axis as range. And we'll move you backward. Okay? What is also important about inverse functions? Cancellation equation. What is cancellation equation? You remember my picture? Range and domain. So direct function takes x and brings it into y. Inverse function takes y and brings it back into x. So the result of applying inverse and direct function to the number is going to be the number itself. So you take a function f of x and apply to the result, which is going to be y, f inverse. The result of your inverse is supposed to be equal to x. It's called cancellation equation. So inverse and direct function cancel each other when they are applied as composition. Similar cancellation equation works if you apply first inverse function. So first you take the y from here and apply inverse, and then take the result and apply direct function. You go back to y. Well, we are going to call it x, but it does not change the fact that they cancel each other. Simple example of cancelling. Well, imagine that my f function is x squared and my f inverse, it's a square root of x. If I apply first f and then take a square root f inverse, I'm going to just get x. It's not going to be exactly x. Actually, I cannot extract square roots of negative numbers. It's going to be absolute value, but for positive x's, where this one exists, it's going to be x actually. If you take first the square root, so inverse function like this, take apply inverse function and then apply direct function. you are going to get x again. Now, how it works in trigonometry. In trigonometry, all our functions are periodic, so they are not one-to-one by definition. If they intersect somewhere, horizontal line, they're going to intersect this horizontal line many, many times. We're going to start with inverse sine function. Inverse sine function. Imagine that we have a sine, everyone remembers, snake shape going on x-axis, x here, y here, 1 here, negative 1 here, right? 2 pi over here. If I draw here horizontal line within range, I don't draw a horizontal line here, it's not going to intersect anything, but it's not going to either have axis, right? But horizontal line within range is going to intersect the function infinitely many times, not 2 or 3, but as far as it goes to infinity. And all these axes are different, and y is going to be same for all of them. So function is not one-to-one. Well, people still want to know inverse. Why? Well, because they want to go back. So they decided, why don't we cut the function a little bit and consider truncated part of sine function. They're going to cut it here and cut it here. Actually, we are going to have all possible values of range and some values in domain. I'm going to graph the sine function which we are going to cut. I'm going to graph it a little bit bigger. So it's pi over 2 here, it's 1 here, negative pi over 2 here, and minus 1 here, x here, and y here. So that's part of the sine for which we can create inverse, because this one is one-to-one. One-to-one intersects horizontal line only once everywhere. So we are going to create inverse, and our inverse is going to be called sine inverse of x, or another name people are using sometimes, it's arc sine of x. Why do we have such a strange name, arc sine? Well, remember, direct function sine takes an angle theta and returns a number, which is actually arc length, right? So, what inverse is going to do? Inverse function is going to take a number and return an angle. So, it's kind of returning the arc. And that's why we call it arc sine. People are using equally this and this because sometimes this minus 1 looks like the power of negative 1, and people don't want to get confused, so they write down arc sine, give a different name to the function. Sometimes like exponential function and logarithmic are inverses, but they don't have the same name. Okay, now how inverse function graph is going to look? Remember, I was telling that range and domain of inverse function are exchanged. For example, we have over here domain from negative pi over 2 to pi over 2. So it's going to become a range of our sine inverse. For sine inverse, it's going to be a range. We have range of the function from negative 1 to 1, right? And that's going to create our domain. I will try to just graph inverse function, maybe using the very same graph, just using the idea that points are going to switch x and y. So it was like point over here, which had coordinates x and y. Now, because y is becoming our domain and x is becoming range, we are going to graph y here and x somewhere, let me see, somewhere, no, y is not here, y is over here, and x somewhere here. So we are going to get a point which is symmetrical to this one. Actually, the symmetry is going to be about y equals x line. I'm going to graph it, y equals x line. And points are going to be symmetrical about this line. What does it mean? For example, the point which sits on the line is not going to change anywhere. This point is not going to change, and this point is not going to change. So I'm going to just draw how the curve is going to look. Sorry, it went up too much. The curve is going to look like this. What is going to happen to this point? Coordinates are minus 1 pi over 2. It's going to become point minus 1 here. This minus 1 goes here, and pi over 2 will go over here. point is going to be over here. Pi over 2 minus this point, coordinates pi over 2 and 1. It's going to have the y coordinate pi over 2. By the way, pi over 2 is 1.5, somewhere around this, because pi is 3.14, right? And 1 is going to be somewhere here, 1. We're going to have something like this. I'm going to graph now it separately so everyone can see how actually inverse sine is going to look. And write down range and domain for inverse sine one more time, so you will need to kind of remember it. So, sine inverse. Minus 1, pi over 2, negative pi over 2, x and y. So, sine inverse of x, domain, from negative 1 to 1. So you can put instead of x only numbers from negative 1 to 1. You cannot put over here 3 or 100. It's not going to work. Sine inverse is not eating anything beyond these two numbers. Range. Well, range is from negative pi over 2 to pi over 2. These are going to be the numbers which sine inverse is going to return. So sine inverse will never return you pi or 3 pi over 2 or anything greater than pi over 2. And anything smaller than negative pi over 2, for example, negative 5 pi over 2 will never return it. So it's going to return only numbers from this interval. Okay, so why do we need inverses? We need inverses to find angles. Let me erase this graph, we don't need it anymore, and talk a little bit of like the destination of inverses. Why do we need them? Imagine sine of theta equals 1. And somebody is asking, what is theta? Well, theta is actually sine inverse of 1. Theta is producing 1, so inverse function will take 1 and return you back theta. Well, we do remember that sine of pi over 2 from the table equals to 1, right? So we actually know that theta equals pi over 2. Well, what does it mean? That's going to be the value for inverse function. Sine inverse of 1 is pi over 2. Okay, so that's how are we going to use inverses, and let's just like give a couple of more examples of that. Now let's try to figure out what is sine inverse of 1 over square root of 2. Remember that this is sine of some angle, and sine inverse is going to give us this angle. So sine of which angle is this? Well, if you recall the table, that's sine of pi over 4, right, or 45 degrees. This is sine of pi over 4, which means that inverse of this number is going to be pi over 4. Is it always going to be a number here from a table? Not necessarily. You actually can have something like this. Sine inverse of 1 over 3. And there is no 1 over 3 in our table of sines. We do have 0 there, we have square root of 3 over 2, we have 1/2, 1 over square root of 2, we have 1, but we don't have 1 over 3. So, how do we calculate this? You just take a calculator. And, well, depending on what the problem is asking, radians or degrees, you set it up in a certain mode, radians and degrees. And then just enter sine inverse of your number. Usually sine inverse is going to be like a secondary function applied. Normally you have the buttons named sine, and sine inverse is going to be a secondary function. For this one, the result is 0.34 radians. But, well, I did not calculate it actually, I just took it from the book. What else can we calculate using sine inverses? How we can use it? Well, let's practice a little bit with use of cancellation equations. For example, somebody is asking us, what is exact value of sine inverse of x? We remember cancellation equation, f over f inverse supposed to give us x. And the second cancellation equation is going to be sine inverse over sine of x. So two cancellation equations. Direct function inverse over x is going to return you back x. Inverse function over direct over x is going to return you back x. Let's apply it to something. For example, sine inverse of sine of pi over 2. What is going to be? Well, let's first calculate it and then check. Does the equation work? What is sine of pi over 2? Well, sine of pi over 2, everyone remembers it's 1, right? Sine of pi over 2 is 1. What angle will give you sine equals 1? Well, pi over 2. You see, cancellation equation is working. Let's use it opposite direction. Sine of sine inverse of 1. Well, we're supposed to get 1, but are we going to get 1? What is sine inverse of 1? We already know that sine inverse of 1 is pi over 2. Right angle pi over 2 will give you sine equals to 1. Now we apply this sine to pi over 2 and we get 1 again. So it's not actually a question anymore. That's a fact. So this is how cancellation equations are working. Now, what if the argument is not very nice? We had just a nice argument like pi over 2 or 1, right? Let's consider slightly different arguments. What if we want to calculate sine inverse of sine of 2 pi over 3? Well, normally using cancellation equation, we just have to write down 2 pi over 3, right? But we remember that a range of sine inverse, or what it's going to produce, is always going to be from negative pi over 2 to pi over 2. Obviously, 2 pi over 3 is greater, because if you draw the picture, sine inverse is going to produce angles from here to here, from negative pi over 2 to pi over 2. 2 pi over 3 sits somewhere here. This is 2 pi over 3 angle. You see, it's not going to actually, sine inverse is not going to give you this angle. Well, how do we solve this problem? We recall that sine of 2 pi over 3, remember what is actually sine? Sine is y-coordinate, right? If you draw a unit circle, y-coordinate for 2 pi over 3 is going to be same as y-coordinate for which angle? Just pi over 3. We're going to just have same coordinate just because they're symmetrical points. I'm going to write down sine of pi over 3. Now I'll put sine of pi over 3 instead of this into my equation. Sine of pi over 3. Now I can apply cancellation rule, and the result is going to be within domain or within range of sine inverse. You see? Well, you have to be careful when you use cancellation equation. Remember about ranges and domains. What else? Let me erase this example. Now let's switch the functions and see what kind of tricky problems expect us on this road. Let's consider sine of sine inverse of 2. According to cancellation equation, we can cancel everything and just get 2, right? Well, we do remember that sine, which looks like this, will never go above 1, right? It cannot return you 2, no matter what. And you start thinking, okay, what is wrong with this equation? Let's look at this one, sine inverse. Remember I was talking about domain of sine inverse. Domain of sine inverse of x is what? Negative 1, 1, right? The possible axis which you can feed the sine inverse. Remember, sine inverse was looking like this, and this was 1, and this was negative 1. So we could not actually go to 2. There is no function at 2. 2 sits over here, function ends over here. So this function is undefined. And you are just going to answer undefined. You cannot calculate it because actually the original function is undefined, and you cannot apply sine to undefined function. Okay? Now, I'm going to write down 4 problems to solve on your own. I'll give you 2-3 minutes maybe. They're easy problems, and check the answers. Okay? So let me erase everything. You can pause the video during this time and take more time to solve the problems. So they're self-problems. A. Sine inverse of sine of pi over 3. By the way, not all problems are tricky. B. Sine inverse of sine of 5 pi over 6. But some are tricky. Sine of sine inverse of 0.5. And the last one is sine of sine inverse of -3. Okay, let's do the solving. We're going to stop for a second. I'm going to, of course, return right away, but you can stop the video and try to solve it on your own, okay? So that's my pause. I think I'm going to start solving backwards with problem Z. I'm going to see that sine inverse is applied to -3, but I remember that sine inverse, it's only numbers from -1 to 1. So we cannot apply it to -3. This is undefined. And you can put it as an answer over here. But this one, is this one within domain? Yeah, it's within domain. It's sitting between -1 and 1, so I can use cancellation equation and get a very simple answer, 0.5. For this, sine can be applied to 5 pi over 6, right? But if you just cancel sine and sine inverse, you are going to get 5 pi over 6, which is not correct, because sine inverse returns only numbers from -pi over 2 to pi over 2. And 5 pi over 6 is not there. I'm going to draw the graph, so we can use only numbers from here to here, but 5 pi over 6, it's actually over here. What should I do? I'm going to erase 5 pi over 6 and think. Okay, because it's a sine for 5 pi over 6 is going to be equal to some other sine of some other angle. If this is 5 pi over 6, so little angle over here is just pi over 6, and that's going to produce the same y. So I'm going to use this fact and substitute instead of this expression sine of pi over 6. Now, if I cancel sine and sine inverse, I'm going to get pi over 6, and pi over 6 sits well within the range of sine inverse. Now, last one. Imagine we cancel sine and sine inverse, we get pi over 3. Is it within range? Yeah, it is within range, so everything is going to work. So these are my answers. One undefined, one, the rest of them, one is just pure cancellation, another one is pure cancellation. This one, a little bit of work. Okay, and we are going to move to cosine function, which is going to be in a different video. Thank you. Hello everyone. This is my, I don't know, maybe 5th attempt to make up a video lecture. So we are going to start from the place we stopped last class. We are going to consider inverse function to cosine. So direct function y equals cosine of x. We do know that the function is periodic. Periodic means that it's going to have infinitely many intersections with any horizontal line within the range, right? And this function is obviously not one-to-one. Not one-to-one. So it's not going to have inverse. For inverse to exist, for every y, we're supposed to have only one x, right? Over here, over here, over here, we are going to have lots of different x's. So there is no chance for this cosine to have inverse. We have to do the same stuff we did with sine and cut part of the cosine, which is going to be one-to-one. If you look at the picture, the best part is going to start at 0 and up over here at exactly where? Pi. So from 0 to pi we are going to have a piece of cosine from 0 to pi. Let me redraw that, please. It's going to look like this, 1 over here, and something like this. Over here is going to be -1. Over here pi, and here pi over 2. Doesn't look very proportional, but still not bad, right? That's a part of cosine which is now one-to-one, has inverse. And inverse of this cosine is going to be, half inverse is going to be cosine inverse of x. Also in some books you are going to have arc. Arc cosine of x. Different way to write down cosine inverse. Okay, how this cosine inverse is going to look on the graph? Well, we remember that inverse function is exchanging x and y. So, for example, for the point over here, we do have a 0 for x and 1 for y. Now the inverse point is going to be 1 for x and 0 for y. Somewhere here. This one is y equals 0, x equals pi over 2. So we're going to couple with the point over here. For this one, it's a bit more complicated. We will need to actually find out where the point is going to land if I make a reflection of the point around y equals x line, but still going somewhere here. And the picture is going to look like this. Looks very similar to sine inverse, just sine inverse is going to be from negative pi over 2 to pi over 2. And it's going to be increasing one, this one is decreasing. What do we need to know about cosine inverse? The domain are possible axes. Well, we see the possible axes here are going to be from negative 1 to 1. Negative 1 to 1. So you can plug in negative 1 to 1 over here. You cannot plug in 2 over here because there is no angle which is going to produce cosine which is equal to 2. Range, possible values which are returned by cosine are the angles. And because we were choosing the angles from 0 to pi, they are going to be from 0 to pi. Okay, example. For example, cosine inverse of 1/2. Well, how do we find cosine inverse of 1/2? Well, first we have to think, okay, which angle is producing cosine, which is equal to 1/2? And recalling our table, we are going to kind of think, okay, I'm probably going to be pi over 3. Write down pi over 3. So that's how we find inverses. What else we need to know about the cosine inverse? Cosine inverse has same cancellation equations as sine inverse. Let me erase something from over here and write them down. So cosine of cosine inverse of x is going to be equal x. Also, cosine inverse of cosine of x is going to be equal x. Well, x supposed to be in domain. This x in domain of cosine inverse, and this x, well, can be actually anything from 0, from negative infinity to positive infinity. But cosine inverse is going to return the angle which is going to be only from 0 to pi. The result here is going to be. Okay, what I'm going to do, I want to make a table for cosine and cosine inverse for comparison. And then maybe we calculate several cosines and see what kind of tricks we can have with cosines. Okay, so let's try. So our table was looking like this, theta and cosine of theta. I'm not going to do the whole cosine from 0 to pi. I'm just going to start 0 to pi over 2. So 0 at 0 is 1, right? Pi over 6 is square root of 3 over 2. Pi over 4 is going to be 1 over square root of 2. Pi over 3 is going to be 1/2. And pi over 2 is going to be 0. What is going to happen for inverse function? For inverse function, everything is going to change. So for example, this column, which is y, actually is going to become my new x here. So I'm just going to copy it. Square root of 3 over 2, 1 over square root of 2, 1/2, 0. And this column I'm going to copy over here, and that's going to be my new table for inverse. Pi over 4, pi over 3, and pi over 2. So now if somebody tells me, what is cosine inverse of 0? I'm going to tell him, it's pi over 2. So 0, cosine inverse, pi over 2. Okay, well, I don't know, maybe we should try something, a couple of examples of cosine. Let me interrupt the video and erase everything from the board and then do that. Okay, we see on the board two examples of use of cancellation equations. Example number 1, cosine inverse of cosine of pi over 12. Normally, you just cross inverse and direct function and get the result, which is your x, argument of the inner function. We'll need to make sure that the argument fits into the range of cosine inverse. Range of cosine inverse is from 0 to pi, so our argument fits into it. Opposite.
cancellation equation, we have direct function and then inverse function of negative 0.4. So again, do cancellation, check if argument fits into the range of cosine. Range of cosine is from negative 1 to 1. Negative 0.4 fits into the range, so everything is fine. Now, slightly tricky question. Cosine inverse of cosine of negative 2 pi over 3. Well, normally we would cancel cosine and cosine inverse and get negative 2 pi over 3. The only one problem over here is that negative 2 pi over 3 does not fit into the range of cosine inverse, so we cannot use it. So what we can do actually, we will need to find the corresponding angle which is going to have the same x as minus 2 pi over 3. Well, first, what is minus 2 pi over 3? That's a negative angle. Negative means that clockwise, and somewhere here 2 pi over 3, right? So minus 2 pi over 3. We remember that the cosine is x coordinate, right? So x coordinate is somewhere here. So what other angle is going to produce the same x coordinate? Well, just imagine a symmetrical angle to this one. It's going to produce the same x coordinate. What is the angle here? 2 pi over 3. So that's going to be the answer actually, 2 pi over 3. And this 2 pi over 3 is going to fit to our range. Well, try some problems from the homework at this time. Hello everyone, we are going to continue our video lecture course. We are moving to the last inverse function we're going to learn, and that's going to be tangent inverse. So let me write my tangent of x and see how inverse is going to work. Well, that's a tangent, right? Tangent is also a periodic function. So I'm going to lots of other tangents. What we see is if we draw a horizontal line, it's not going to pass it again. Many times intersection, right? So we're going to truncate our tangent into one period of tangent only. And this time it's not that difficult. Let's look at it. 1, 2. That's going to be only tangent we're going to consider, x and y. So for this one, it's going to pass horizontal line test, and we can easily create inverse. I'm going to graph inverse tangent. Remember that it's a reflection around y equals x line. So we are going to reflect everything. For example, we are going to first reflect vertical asymptotes. Vertical asymptotes reflected are going to become horizontal asymptotes. And like this. They go through pi over 2 and negative pi over 2 here. And the graph is going to be looking like I just put it horizontal. That's tangent inverse. What is interesting about tangent? It goes from negative infinity to positive infinity in x-axis. In comparison to sine and cosine, which were very limited in their means, tangent is going to go from negative infinity to positive infinity. The range of tangent is still limited. The range is going to be not included, sorry, from negative pi over 2 to pi over 2. And that's how the tangent inverse is going to look. How it's going to look as a table, let me just write down the table over here. So if it's theta and it's tangent, I'm going to do only half of the tangent, which is positive. At 0, 0, right? That pi over 6 is 1 square root of 3. Pi over 4 is 1. And pi over 3 is going to be a square root of 3. And pi over 2, it's going to be amplifying, right? So what is going to happen to tangent inverse? Let's put x here and tangent inverse here. Well, I'm going to copy this comma over here into x. I'm going to put undefined here. So what are going to be tangent inverses? Well, the angle which is producing tangent equals to 0, 0, right? The angle which is producing tangent 1 over square root of 2. That's pi over 6. This is pi over 4. This is pi over 3. Well, that's not actually the angle pi over 2 going to produce undefined, or undefined x is going to produce pi over 2. We're just going to remember that when x goes to either positive infinity or to negative infinity, the value of tangent inverse is going to approach pi over 2, but it's never going to be equal pi over 2 because it's asymptote, right? Well, that's the last function, tangent. I'm going to raise the top of tangent and kind of show cancellation equations for tangents really quickly. How are they going to work? Well, we remember that they're looking like this. Tangent of tangent inverse of x equals x, right? And tangent inverse of tangent of x also is going to be equal to x. So kind of they cancel each other, and the only leftover is r. Now, how it's going to work on numbers? Well, I don't know. Let's try this one and pick up something from over here. For example, I'm going to write down tangent of tangent inverse of, I don't know, let's do 1, for example. Tangent inverse of 1, tangent inverse of 1 is pi over 4, right? This one is pi over 4. It's producing tangent equals to 1. Tangent of pi over 4 is going to be 1 again, so 1 is equal to 1. Let's do an example of this cancellation. Tangent inverse of tangent. Well, let's imagine that we have a tangent of pi over 3 here. So what is tangent of pi over 3? Tangent of pi over 3 equals the square root of 3. Tangent inverse of square root of 3. Tangent inverse of square root of 3 is pi over 3. And we're getting it back. Well, basically, that's it. If you do have any angle over here, which is beyond negative pi over 2, so you are not going to get anything more than pi over 2 or less than negative pi over 2 as a return value from tangent inverse. Well, we'll need to just adjust the angle and see where it's going to be. Let me show you how it works once. I don't know, let's choose something like maybe tangent inverse of tangent of 2 pi over 3. So, is it going to be 2 pi over 3? We remember that tangent inverse can return us only values from negative pi over 2 to pi over 2. This is definitely greater, 2 pi over 3. So how are we going to deal with this? So what is 2 pi over 3? 2 pi over 3 is the angle over here. And, well, we can be only over here, so we need to figure out like what kind of angle we are going to have. For tangent, we are going to continue this line here and see what is going to be the angle which corresponds to this one over here. And that's going to be the angle minus pi over 3. So I'm going to have minus pi over 3 over here. Okay, and the next piece of information from this section is how to find inverses of trigonometric functions. Let's first review how to find inverses in general. For example, somebody gives us a function f of x equals 2x plus 3. How do we find f inverse, if it does exist? Well, the steps are 1. Set up y equals 2x plus 3. Step number 2, exchange x and y and have it as x equals 2y plus 3. Step number 3, solve for y. Solve for y means that y is going to be variable, x is going to be kind of everything else is known. So I'm going to have x minus 3 equals 2y, x minus 3 over 2 equals y, and that's going to be my inverse. So my inverse f inverse equals x minus 3 over 2. Now I'm going to apply the same technique to finding inverse of trigonometric functions. Look at it for a second, and I'm going to erase it. 1, 2, 3. Out of x, I'm not going to modify it a lot. I'm going to write down 2 sine of x minus 1. So somebody is asking me to find the inverse of this function. Inverse of the question. Well, I'm going to use the very same steps. Y equals 2 sine of x minus 1. Then number 2, exchange x and y. It's going to give me x equals 2 sine of y minus 1. And then I'm going to solve for y. X plus 1 equals 2 sine of y, right? I'm going to divide by 2 both sides, here by 2. And I need to find the y. I do know sine of y. How do I find y? Well, I take inverse of both sides. Inverse sine of x plus 1 over 2. And here I'm going to have sine inverse of sine of y. I know that inverse and direct function cancel each other, and I'm just going to get y. So y equals sine inverse of x plus 1 over 2. And that's how we find inverse. Maybe I should give you something for practice. Let's see anything good in the book. Oh, right. I know something. Okay, let me erase this. I'm going to put a practice problem on the board. At this moment, after you see the practice problem, you can stop recording and try to solve the problem first on your own, and then see how I solve it. So f of x equals 3 tangent of x plus 2. So the question is to find inverse. So at this moment you can stop recording. I'm going to wait 3 seconds and do solution. You can do solution and then look at the rest of the recording. Okay, so I'm going to write down y equals 3 tangent of x plus 2, and then exchange x and y as x equals 3 tangent of y plus 2, and now I'm solving for y. So it's x minus 2 equals 3 tangent of y, x minus 2 over 3 equals tangent of y, and the last step to get just y without tangent is to take tangent inverse on both sides. So tangent inverse of x minus 2 over 3 equals tangent inverse of tangent of y. These two cancel each other, and I'm going to just get y here, and that's going to be my inverse function. And you can write it down separately, like f inverse equals tangent inverse of x minus 2 over 3. That's going to be the final answer. Now guys, I want you to practice with homework a little bit. Please watch the restrictions on range and domain of sine inverse, cosine inverse, and tangent inverse. Try to figure out what to do one more time when you go above or beyond the possible range or possible domain. Okay, that's all from section 2.1, and our next lecture is going to be on 2.2. Thank you very much. Hello everyone, I'm going to start recording section 2.2, inverse trigonometric functions. From this section we are going to do only first 3 examples, example 1, example 2, and example 3. I'm going to teach you how